Okay, what are eigenvalues? They're like values of lambda in the equation 0.9 minus lambda, 0.2, 0.1, 0.8 minus lambda, determinant of equals 0. Okay? Now, there's a lot of profound meanings to eigenvalues. How many of you have had chemistry? You know their energy levels, right? Well, those energy levels come out of eigenvalues. Okay? They come out of eigenvalues of a certain matrix calculation, quantum mechanical calculation. Okay? And so do all the energy levels of that uranium atom that you've worked out. Anybody get that on the trip? You know, when you're just not doing anything, you know, you kind of get a little sleepy and you dream the answer, and then you kind of forget it when you wake up, but you quick write it down and you get it, right? So most of you got that, right? Okay, did anybody write it down real well, or do you still want to write it down better so I can understand it and take credit for it? Well, whatever. Remember, it's at least an A minus if you just solve the problem, right? Become the first one in the world to solve it. Okay? Okay, well, keep working on it if you don't have it. Okay, well, anyhow, it's just an eigenvalue problem, but your matrix would be 100 by 100. Okay? Now, what's the equation you get from this? Well, I believe the equation, if you do the determinant, is this times this minus this, right?
Yeah.
So I believe that's lambda squared minus 1.7 lambda plus 0.7 equals 0, right?
Mm-hmm.
You can find the values of lambda. Okay? Just plug this into the quadratic equation and you've got it. Okay? So here's a very simple scheme for eigenvalues. Now if it's a 100 by 100 matrix, then this first lambda is going to be to the 100th power, and the next will be to the 99th, and it'll be a big long polynomial, but all you got to do is factor it. Well, even when you get up to one more dimension, a third dimension, okay, you can't necessarily factor the thing easily, okay? There is a scheme. You can always solve a third degree equation. Kind of like the quadratic formula, but quite a bit more complicated. And there's even a formula for fourth degree, which I've never even seriously looked at. It's pretty complicated, but you know, if you practice it a while, you can learn to use it. Okay? And one of the great results of abstract algebra, it took until the late 19th century before anybody figured out why you can't always solve a fifth degree or any higher degree. It's impossible. Okay? And that's a big deal because there are all kinds of implications of that theorem. But the point is, you can't solve anything better than the fifth degree, right? You might be able to solve it. There's certainly, you know, lambda to the fifth equals 1. Can you solve that? Well, yeah, lambda is 1, right? 5 times lambda is 1. You have 5 solutions. They all say lambda equals 1, right? Okay? But if you just write down random numbers in front of your lambda to the fifth and lambda to the fourth and so forth, chances are that it can't be solved by any method. It can be approximated by methods that, you know, we're not going to do much with because you've got to really, really, really understand graphs and polynomials, okay? But, you know, the computer algebra system can approximate those zeros, okay? And then you have your eigenvalues for that matrix, okay? So that's not hard to understand. And nobody knows how to factor a 100th degree polynomial unless you just really get lucky. It's almost impossible that you could even write one down that could be factored. Now you could write down like lambda minus 0.07, lambda minus 0.035, okay? 100 of them and multiply them out using the distributive law and get a 100th degree polynomial, and then take that to somebody and say, hey, I know this factors, but I keep screwing it up. Can you factor it? Cruel joke to play on somebody, but nobody would take that big, okay? At least nobody that knew how to really factor things and do the whole landscape. Okay, so you get the idea? So we're going to do 3 by 3 matrices. Okay, we'll do a little of that this afternoon. You know, you could say, okay, if we have a 3 by 3 matrix, let's just do a 3 by 3 stochastic matrix. Stochastic matrix right now simply means that the columns add up to 1, which will be the case for any of these that don't lose bugs on the ends. If they lose bugs on the ends, they're no longer stochastic. But notice that this column adds up to 1, this column adds up to 1, and this column adds up to 1. Only this column doesn't, and that's because the first tree is losing bugs, right? If you put another element in here that keeps track of the bugs that get lost, then of course you got 5 numbers here, right? But then you'd have a 5% here, a 0.05, and it would be a stochastic matrix, right? Mm-hmm. Okay, so anyhow, let's, I don't want to write that one down. Let's write one down that might be similar. Let's say you have 0.05, 0.85, 0.1. You know, just 3 trees, 5%, whatever. And then here you have 0.1, 0.8, 0.1. And here, let's say you have 0.1, 0.1, 0.8. Okay, all these columns add up to 1. If this is some kind of a bug model, you're not losing any bugs. You're not losing any energy. You're not losing any of the heat. Okay? Mm-hmm. You're keeping track of how much of the heat goes into the atmosphere. You're not sure where it is after it goes into the atmosphere, but you keep track of it, okay? This is an example. Okay? And then you throw a minus lambda on each element on the main diagonal. And I didn't leave myself room to do that because I'm incapable this morning of anticipating my next step. Okay? Not totally incapable, but I didn't do it that time. Okay, so do you see what I've done? Okay? Well, if you multiply these out, and you don't have to, but if you multiply these out, you're going to get a 3rd degree polynomial, right? Okay? Anybody know what the graph of a 3rd degree polynomial looks like? Yeah. Okay? If you've had pre-calculus, you should certainly know that the graph of a 3rd degree polynomial will typically look like this. Okay? And of course, you set that determinant equal to 0, that's equivalent to figuring out where this graph crosses the x-axis, right? And those points on the x-axis will be your solution. So this would be like lambda 1, lambda 2, and lambda 3. 3 eigenvalues. Eigenvalue 1, eigenvalue 2, eigenvalue 3. Okay? Now you can find the exact values of these eigenvalues. You might not be able to write them out as decimals. They might have some square roots or cube roots in them or something, okay? Mm-hmm. But you could write them out. And the thing I told you about the uranium atom and a lot of other totally apparently unrelated things is that if you have like a big matrix, you have a certain type of pattern that tends to emerge in the eigenvalues, okay? if you do a 100 by 100 random matrix, the pattern is very similar to what you have from your uranium atom or from certain aspects of the internet, etc. Okay? So that's what eigenvalues are. Right now, you got to know that you write down a stochastic matrix, a matrix whose columns add up to 1, put a minus lambda here, and then do the determinant. And you just don't know how to do a determinant of a 3 by 3 matrix. Do you? Some of you might. I mean, this used to be covered. Okay? Not anymore. So that's it. Well, we still have a couple minutes. I'll just give you a quick view of how you do a determinant of a 3 by 3. Yes, ma'am?
Do the determinants, or like the eigenvalues, these have anything to do with the limiting values?
The what now?
I
talk about limiting values?
Yeah, are they like similar to this?
They have a lot to do with the limiting values of the matrix. Okay?
But they're not the same?
Well, yeah, I'm done.